Hi everyone, thank you for joining me on this online learning experience. I'm pretty new with this stuff, so I'm going to be playing around with a few different options I think this week. So today is going to be kind of like Khan Academy style, just writing on a virtual whiteboard. And I might play around with some other options the other days this week, but we'll see how this goes. But please just bear with me. I'm using a new program that I haven't really used before, and I hopefully have worked out most of the details of it, but I'm sure we will hit some kind of obstacle at some point during this recording. Okay, so today what I want to do is basically talk about dimension a little bit more. So I want to review what we were talking about on Friday. I already ran into my first issue. There we go. So I want to start by reviewing what we're talking about on Friday with what the dimension of a vector space means. And I basically just want to go through several different examples of finding dimensions of different types of vector spaces. And then there will be a theorem that we'll talk about towards the end that basically will make it easier to find bases for vector spaces. But yeah, we're going to get started mostly with just a bunch of examples. So I want to start by writing out again the definition of dimension of a vector space. So remember that we talked about this on Friday. The dimension of a vector space is basically the number of vectors in any basis of that vector space. So I'll start to write that out. So if you have a basis B1, B2 through Bn, so Bn basis elements, then that means that the dimension of that vector space is going to be n, is the basis of V. So dim V is our kind of abbreviation for dimension of V is equal to n. And something that kind of underlies this is the fact that we talked about the other day that no matter which basis you look at for a particular vector space, it always has the same number of elements. So for example, we know that you can pick any two linearly independent vectors in R2 as a basis. You could pick 0, 1, and 1, 0, but there's lots of different options. The important thing is that no matter what option you choose, any basis will have the same number of vectors. And what that means is that this notion of dimension is well defined. Like it isn't going to be two different things for any one vector space. One other thing I just want to quickly jot down, and we'll get back to this in a little bit, is that so some vector spaces actually cannot be written as, don't have a finite basis. So if V is not the span of a finite set of vectors, then we say that V is called infinite dimensional. So we don't really say, oh, the dimension is infinity. The word dimension is really preserved for saying, finite number, but we call it infinite dimensional. And we really are not going to encounter too many examples like this, but we'll see one today. Okay. So first example I want to do, we can think of it as kind of a warm-up. So I would recommend maybe pausing the video after I write this example down, trying it yourself, and then we'll go through it together. But I think you'll get more out of it if you try it yourself first, because it is similar to when we did the other day. All right, so let's let H be equal to the span of the following three vectors. So 2, -1, 1, 5, and -3, 4. So the question is basically to find the dimension of that subspace H. So again, pause the video right now, try yourself to sort this out, and then resume the video and we'll see what the explanation is. Okay, so there's a variety of ways that these dimension problems are going to go, but the basic thing is just figuring out what is a basis for the subspace that you're talking about, because once you have a basis, then you can find the dimension. So in this case, we have 3 vectors in our span, or we have the span of 3 vectors rather, and they're all vectors in R2. And we can see that the first 2 are not multiples of each other, right? Neither one is a multiple of the other. Whereas the third vector, then we can see, is a linear combination. It's just the sum of the first 2 vectors. And that's going to be the case for really any 3 vectors in R2. There's no way that all 3 of them will be linearly independent from one another. So what we have is 2 vectors that are linearly independent, and then as soon as we throw in the third one, it becomes a linearly dependent set. So we could actually pick and choose which of these 2 we want to take as our basis, but let's just take the first 2, for example. So basically what I'm saying right now is that the span of these 3 vectors is the same thing as the span of just the first 2 vectors, because the third vector doesn't contribute anything to that span. Because the third vector is already a linear combination of the first 2 vectors, it just doesn't add anything. However, because these 2 vectors that we're left with in this new set, those are linearly independent, what that means is that we can't kind of go any smaller without changing our subspace. So the span is actually equal to R2. Because we have 2 linearly independent vectors, each with 2 components, that gives us all of our 2. And so the dimension is going to end up being 2 because we have 2 basis vectors. And I mentioned this in a similar example on Friday, but just to kind of write it down, we could have picked, once you know that the span of those 3 original vectors is all of our 2, you can pick any 2 vectors that you want, as long as there are 2 linearly independent vectors in R2 as your basis. So even though these 3 sets of vectors that are written down here are different sets, their span is the same. So the span of these 3 sets is exactly the same. However, there's a key difference, which is that the first example, so this set here, this is not a basis. And the reason that it's not a basis for H, or H, so H is actually equal to all of R2, right? So we can either call it H or R2, it doesn't really matter. But this is not a basis for H because it had that kind of extra information. However, these 2 bottom ones, these both are bases for H. And I mentioned this, I think, on the first day we talked about basis, but the plural of basis is bases with an E. So these both are bases for H. And they both have 2 elements, and so what that tells us is that the dimension of H is equal to 2. So the reason I gave an example that was like this was to point out to you that the dimension doesn't depend on how many vectors are given to you in that spanning set. We could have even had 4 or 5 or 6 vectors in the spanning set. What matters is how many of them are actually linearly independent. And so in this case, it came down to really just having 2 linearly independent vectors, and so therefore we have a dimension of 2. All right, so we're going to try another example, kind of similar, but slightly different setup. Oops. Let's see. Okay, there we go. So, example. So this time, let's call our subspace W. So let W, actually I'll write this out in words. So W is going to be a subspace of R4. So let W be the subspace of R4 consisting of vectors. Sorry if this writing gets a little glitchy. Vectors of the form. So this is going to be kind of a big vector. Okay, so our first component is going to be A minus 3B plus 6C Second component is 5a plus 4d. Third component is b minus 2c minus d. And then the fourth component is 5d. And so we have vectors of this form where basically a, b, c, and d are allowed to be any real number. So I'll just say that as for real numbers. So a, b, c, and d are basically varying. And so just like with our last example, the goal is going to be to find the dimension of W. And by the way, feel free to, at any point in this video, if you want to pause it and try to do it yourself. I think that's always a good thing to try. I said it explicitly for the first example because I think it was a slightly simpler example. But yeah, definitely feel more than welcome to pause, fast forward, whatever you got to do to make the most out of this video. Okay, so the approach we're going to take on this is pretty similar to some examples we saw back when we were talking about subspaces, where in order to see the spanning set of this subspace of vectors, we're going to kind of separate out the A, B, C, and D, because that will allow us to see kind of in parametric vector form. That will allow us to see what are the vectors that we're actually kind of combining in order to get vectors of this form. So we're going to write A times, and then just kind of look through and see what we need from each part. So we have 1 in the first component, 5, 0, 0. We have, then for B, we have -3 in the first component, 0 in the second component, 1, and then 0. And then we have 6, 0, -2, 0. And then we have D times 0, 4, -1, 5. Hopefully I did that all right. So remembering the fact that A, B, C, and D are all just any real number, basically what we figured out by writing it down this way is that our subspace W is actually just equal to the span of those 4 vectors, because the span is literally just the set of all linear combinations. That's what the word span means. And so what we wrote down above is the span of these vectors. So we have, -3, 0, 1, 0, 6, 0, -2, 0. Okay, so our 4 vectors. And you might think like, okay, we have 4 vectors. Potentially this could actually be all of our 4. But by looking at the vectors, we can see that actually the second and the third one are scalar multiples of each other. And so what that means is that the span of these 4 vectors is really the same thing as the span of just taking, I'll just take maybe the first of those two. So I'm going to take out the 6, 0, -2, 0 vector. So it's kind of, it's basically very similar to the first example we did where we took out one vector because we just didn't need it. It was not adding any information to this span. So in some cases, so actually, maybe let me say first, so looking at these 3 vectors we have, these now actually are linearly independent. And there might be some cases where you have to do a little bit more work to kind of figure out whether they're linearly independent or not. Like you could, solve a homogeneous system of equations to confirm whether any set of vectors is linearly independent or not. In this case, I think just by kind of looking at them, you can see that because of where the zeros are positioned, you just really can't combine any 2 of these to get a third one, or to get the third one. So what this tells us is that we're kind of down to the minimum or the minimal spanning set. And so that means that the dimension, or that means that our spanning set that we just found is a basis. So this set here is a basis for our subspace W. And because that basis has 3 elements, that means the dimension of W is 3. So it's a 3-dimensional subspace of R4. Not necessarily something you can actually imagine, but yeah. And so in this case, it does matter. So like, for example, on the last one, because the span was all of R2, you could have picked like any 2 linearly independent vectors to make that basis. In this case, I'm not saying that these are the only 3 vectors that you could have chosen. You know, for example, you could just make a scalar multiple of each of them and then make a new set of 3 vectors, and that would also work. But you don't really have any other obvious choices, I guess I'd say. So the vectors that we're working with, because they define a unique 3-dimensional subspace of R4, like if we picked 3 completely other different vectors, it would be a different 3-dimensional subspace. So we do want to kind of stick with these 3. Okay, so let's talk about a couple things that we mentioned last time that I want to just kind of remind you about because they're important. So just talking about the dimension of a few different important vector spaces. So I'll write that, dimensions of important vector spaces. So first one seems kind of maybe obvious because of the way that we use the word dimension in our everyday language, but the dimension of Rn is n. You know, for R2, you only need 2 basis vectors. For R3, you need 3, etc. So the word dimension in this case really kind of coincides with what we think of as dimension, right? We think of 2-dimensional space, 3-dimensional space as a certain thing, and that really does work in this context. Another one that we talked about last time was that if you have the vector space of polynomials of degree at most n, the dimension actually comes out to be n plus 1. And so that's because a basis for something like this, you have to have a constant and then the linear term and then the quadratic term. And because of that extra constant term, you're going to end up actually having n plus 1 elements instead of just n. So another one we can mention now is, and actually let me maybe phrase this a little bit differently. So I'll ask this as a question. So what is the dimension of just P? So if you write P like this without any kind of a number, any kind of like a subscript, that means that you're literally talking about the vector space of all polynomials of any degree. So this is the vector space of all polynomials of any degree. So you could have, you know, x to the 1000 power plus 5x to the 300 power, you know, literally any example of a polynomial that you could cook up with real coefficients. And so if you try to come up with a spanning set, you're just not going to be able to do it, actually. There's no finite set of vectors that will be able to span a vector space consisting of all polynomials of any degree. Like, let's say that you try to make a spanning set where you go up to x to the 100, right? You might guess maybe that's enough. Let's just do x, 1, x squared, x cubed, all the way up to x to the 100. But then what about the polynomial that has x to the 101? So you're just never going to be able to come up with a finite spanning set. And so this is an example of an infinite dimensional vector space. So P cannot be spanned by any finite set of polynomials So P is what's called infinite dimensional. Cool. So one last thing I want to mention before we move on to another more kind of quirky example is just the subspaces of different dimensions of R3, because these are the ones that we can really kind of picture. So I just want to write this down. I think most of this will be pretty intuitive, but just to kind of make it official. So basically R3 can have subspaces of dimension 3, which would be all of R3, dimension 1, dimension 2. So I want to write each of those, dimension 0 as well. So we'll get there in a second. So the 0 dimensional subspace. So we talked about this briefly when we introduced dimension, but the dimension of what's sometimes called the trivial subspace, so the subspace that only contains the 0 vector, that has dimension 0. And that's actually the only 0-dimensional subspace there is. So the 0-dimensional subspace is just the set that only contains basically the origin, or the 0 vector. One-dimensional subspaces are subspaces that can be spanned with one vector. And so if you think about what it looks like for one vector, the span of one vector in R3, it's going to be a line, and specifically a line through the origin. So one-dimensional subspaces are lines through the origin. Two-dimensional subspaces, similarly, now you're talking about, shapes that can be spanned by two vectors, and so that we've seen as a plane. So two-dimensional subspaces are planes through the origin. So R3 has infinitely many one-dimensional and two-dimensional subspaces, right? Because you can just slightly tweak where that line it points or where that plane lies, and it will give you a different subspace. But it only has one 0-dimensional subspace, which is just the subspace containing the 0 vector. And similarly, it only has one 3-dimensional subspace, and this is, I mentioned this before, that technically any vector space is a subspace of itself. It's kind of not the most interesting type of subspace to talk about, but basically the only 3-dimensional subspace is all of R3. So you could do something similar in R2, right, and talk about 0, 1, and 2-dimensional subspaces, but it's not quite as interesting. But then as soon as we go up to R4, you can write this stuff down, but we can't really talk about what it looks like, because we don't really know what 4-dimensional, or at least I don't know what 4-dimensional space looks like. Okay, so I want to do one more example together, and then we will look at a theorem for finding, just kind of helping us with finding bases. So, oops. Okay, so I want to do one more example, like I said. So this is going to be a slightly different type of example, and maybe will help you with something on your written homework. So let's look at a transformation that goes between, so it's transformation from the vector space of all 2x2 matrices with real entries to that same vector space, and the transformation is going to be defined by T of A, B, C, D. So a typical element that you might plug into this transformation would be a matrix A, B, C, D, and what's going to come out is 0, 0, C, D. And so the question that we want to answer here is we want to find the dimension of the kernel of T. And so what that means is we're going to need to figure out what is the kernel of this linear transformation. So what are the types of matrices that are sent to the all zeros matrix. And then we're also going to need to figure out a basis for that kernel. And so once we have that basis, we can just see how many basis elements there are, and that will tell us the dimension. So basically looking at this transformation, and when people are asking me questions on the one of the written homeworks, both this one and the online homework, there's a similar kind of question to this. And my biggest piece of advice, if you're stuck on something like this, is just try plugging in different things and playing around with it. I think if you're afraid to kind of play around and plug stuff in, you're not really going to get to the bottom of it. So try plugging in, if you want to get a vibe for like how this transformation works, plug in a bunch of different matrices, get a sense of what happens when you plug different things in. But basically, if you're trying to plug something in and get zeros in A and B, the types of matrices that you plug in need to also have zeros in A and B, right? Because I just said that backwards. Rewind. I don't think I have the editing skills to edit that out. So sorry I just mixed up what I was saying. What I meant to say was that in order for you to have zeros in the C and D position, you need to plug in a matrix that has zeros in the C and D position. So basically in finding the kernel, we're trying to answer this. We're trying to figure out, what would you need to plug in order to get 0, 0, 0, 0. And so what I'm saying is that we can start to fill some stuff in here, which is that we can, suddenly stopped letting me erase stuff. Okay, I'm just gonna write on top of it. So what we have started to figure out now is that in order to get the zeros in the bottom two components, we need to have zeros in the bottom two components, because if we look at the transformation, whatever starts out in the bottom two components ends up there. However, in the top two components, we have a little bit more freedom, because we actually have a ton more freedom, because you can plug in anything you want for the first two components and you're still always going to get zeros, because that's how this transformation works. And so that means that we can plug in any matrix with any entries A and B, as long as the bottom two entries are 0, it will be in the kernel. So the kernel, I guess I'm changing colors. So the kernel of T is basically going to be all matrices of the form A, B, 0, 0, where A and B are any real numbers. So to find a basis for this kernel, we want to think about how, what is the smallest number of different matrices we can kind of put together in a set so that we'll be able to come up with all matrices of this form AB 0, 0. And so we really only have two numbers here, right? The 0 and the 0, those are always going to be 0 and 0, but the A and the B can be any two different numbers. So basically the basis for the kernel is going to be the following set: 1, 0, 0, 0, and 0, 1, 0, 0. Because we need to have the freedom to be able to build up any two different numbers A and B that we want in the first two components. And that's why you need to have this 1 and this 1 in the two different positions. And then we don't want to put anything in the bottom two positions, because if you did, then those linear combinations would not give you matrices of the right form. And by the way, this is not the only answer. This is one possible basis. It's probably like the simplest one. But any two matrices that you could add up in different ways to give you matrices of the form AB 0, 0 will work. So this is our basis, and so it has two vectors in it, two matrices that we're calling vectors because we're looking at the vector space of matrices. So the dimension of the kernel of t is 2. All right, so one last thing, and then I will let you go. Let me decide what color I want to change to. I think I'll go back to blue. So this is something that's called the basis theorem. Oops. Oh my gosh, what am I doing wrong? It's just not happy with me. There we go. So basically, so far, when we've been talking about showing that something is a basis, so maybe I'll even write this down because I think it's important. So what I'm about to write down is not itself the basis theorem, it's just some kind of like background stuff. So, so far, to show that something is a basis, we need to show two different things, right? So to show us that is a basis, so if you had like a question that was like, determine whether this is a basis for a vector space, you'd want to look at two different qualities of that set. The first thing you would want to check is whether the set is linearly independent. So the set linearly independent. And then the second thing you would want to look at is, does the set span whatever your vector space is? So maybe here I can say basis of V. So what this basis theorem is going to allow us to do is, if we know the dimension of a vector space, it's going to let us only focus on one of these two things instead of having to show both of them. So basically, now we will see if you know the dimension of V, you only need to do one of the two above things. Oops. 1 or 2. Okay, so now I'm going to write down what the actual basis theorem says. I'm going to switch color to emphasize this change. So the basis theorem says that if V is an n-dimensional vector space, two different things. So the first thing is that if you have any linearly independent set of exactly n vectors, that is going to be a basis. So basically, you don't need to check whether they span. If the number of vectors matches the dimension and you know that they're linearly independent, they're actually automatically going to span, and you don't need to check that. And so similarly, if you have any set of exactly n vectors that spans V, is going to be a basis. So you don't need to also check that they're linearly independent. So I want to look at an example of where you might use this, but basically the idea is that it just cuts down on the amount of work you have to do. If you know the dimension and you know how many vectors you're working with, it's going to make things a lot easier. So let's see if I can get it right this time. So one way you might use this is a situation like this. So we want to show that the following set is going to be a basis for P3. So 1 minus x, 2 minus 4x minus, is that a minus or a plus? I'm going to go with minus. I can't quite read my notes, so I think either way it would be a basis. I just don't know if I copied down the right one. And then 6 minus, I wrote down some weird stuff, so I'm just going to go with it. Sorry, in the book they use t, and I've used x for these vector spaces, so that's why I keep erasing. You can check. This is an example from your book. I don't remember exactly where it came from, but I might have some of the details of this wrong, but shouldn't matter too much for our problem. Okay, so we're going to show that this is a basis for P3. So remember that P3 has dimension 4. We talked about that earlier. We know that the standard basis for P3 is just 1, x squared, x cubed, 4 elements, so we know that P3 has dimension 4. And so because this proposed basis has 4 elements, we can pick. We don't need to show both that it's linearly independent and it spans. We can just pick one of those two things to show. So personally, I think that it would be easier to show that this is linearly independent. So let me maybe write some of these ideas down so you have them written down. So our proposed basis has 4 elements. So we only need to show either that it's linearly independent or that it spans, I guess I should write that. So personally, I think that in most cases, it's going to be easier to show that they're linearly independent. So especially because we have this method that we talked about the other day, which is that we can rewrite these polynomials as their coordinate vectors. And that way we can really just kind of look at them as vectors in this case, it would be R4. And that will make it pretty easy to determine whether they're linearly independent. So let's write the basis vectors as their coordinate vectors. So remember, the way that works is that we're going with respect to the standard basis. So the standard basis, so coordinate vectors, we're going to do that with respect to the standard basis, which is 1x, x squared, x cubed. And we're going to use the coefficients of each of those to write down the components of a vector. So for example, the first vector in our basis is going to be 1, 0, 0, 0. And the second one is going to be 1, -1, 0, 0. And the third one is going to be 2, -4, -1, 0. And then the fourth one is going to be 6, -18, 9, -1. And so once you have them written as vectors like this, you can use any method that you want from all the linear algebra we've built up to this point to figuring out whether these are linearly independent. But again, I think just by looking at them, because of where the zeros lie in these different vectors, we can see that they are linearly independent. So basically we showed that these 4 vectors are linearly independent, and so therefore our set is a basis. We don't need to show that it actually spans all of P4 because we know that it has the right number of elements. Okay, so I think that's about it. I probably went a little longer than the 20 to 30 minutes that I suggested it would be, but yeah, I'm also going to post a worksheet that you can look at. It's just going to have a few questions similar to the kind of questions that were in this, just so that you can kind of try some stuff yourself. I just think that listening to a video, it's a lot less engaging than actually being in class. So hopefully by also getting the chance to practice, that will help you get a better learning experience than just watching the video. So after watching this video, try the worksheet. I'll also post solutions for it, probably actually just on the same document. So give those a try, and then I will be back in your feeds tomorrow with another video. All right, thank you all for your hard work, and I will see you later.